We've defined the curly language in terms of substitution, which means that when you say let x be 5, and there's some other function later f that refers to x, that we can implement that by immediately replacing all the x's with 5 and continuing on. What that means is that when a function f is called later, no matter what happens in between, the call to the f will use 5 where x was in the original function. We actually implement substitution using environments, but the environments are making sure that they implement exactly what substitution does. There's nothing that can happen during these dot dot dots that will change the x to be something different than 5. Plait is actually different from that. In Plait, a variable's value can change. Here's a similar example where I've let x be 5. I have a function f that refers to x. But before calling the function, I'm using setBang with the exclamation mark that says something weird is happening here. The weird thing is state. It's changing the x from the value 5 to the value 6, so that by the time I call the function f, x means 6 instead of 5, and we add 1 to 6, and that's why we get 7 out. We would say now that this variables in Plait have state, and they don't in curly. But our goal is to take a look at state. You don't use setBang in Plait. You're not supposed to use setBang in Plait, but in other languages you do use the equivalent feature all the time. For example, suppose you're writing a Java program to sum a list of integers. So here's a sum method with a list of integers coming in as an argument, and the part that uses state is that the variable t is initialized to 0, but the value of t keeps changing to accumulate the sum of the numbers in the list, and eventually we return the value that ends up in t after we iterate through the list. In Plait, you wouldn't do that. The way we would sum a list of numbers is just with a recursive function. If it's an empty list, you return 0. Otherwise, you add the first to the recursion of the rest. You could write it with typecase or with cond. It works out to be the same. This sum is a little different than this Java version of the sum in the sense that this one is adding up the numbers left to right, whereas this one is waiting till it gets all the way to the end of the list before it actually starts adding anything. If it was important to add left to right, maybe they're floating point numbers, then you would get the same Plait program as the Java program by writing it this way, by having an accumulator t that starts out 0, but every time you recur for the rest of the list, you add the first thing directly to t. And then finally at the end, you return t. So t is an accumulator. We're not changing any given t. For a given call of sum, t means the same thing. But every time we make a recursive call, we get a new t and it can have a new value. It turns out that the machine code generated for this bottom Plait example is going to be pretty much the same as the machine code generated for the Java example. The difference is that there is no notion of state in the surface level for this Plait program, and this is a better way to write things in Plait. So in other words, this use of state that you would do in Java, it's not essential to the problem of summing a list. It's just accidental and the style of Java. We could even write the sum function in Plait using folldel, and it would be again the same code and the same absence of state. Here's another example where state is not really essential to the problem. Here I've written a feed function in Java that takes an aquarium as an array of integers, and it feeds all the fish by just incrementing every position in the array. So this is using state. There's an array that is changing as a result of calling the feed function. And it's part of this Java feed methods interface that it changes that array. But of course, we saw before, if we just want to represent aquariums and we want to feed all the fish in the aquarium, we can do that in a functional way by taking a list of numbers and returning a list of numbers, using map or writing our own list or whatever. So this again is an example where using state is not essential to the problem of representing aquariums and feeding the fish in the aquariums. And avoiding state comes with some advantages. So when we're trying to test our feed function, we can feed and give it a list and just check that the result list is the right list. We don't have to set up an array and then check that how that array is changed afterwards. Another advantage of avoiding state is that when we feed today's fish and get tomorrow's aquarium, then we still have today's aquarium. So we can compare today's aquarium and tomorrow's aquarium. Feed doesn't have the effect of destroying our old array to change it into the new array. We get to keep both of them and use them both if we want to. So there are good reasons to avoid state. On the other hand, there are cases where state is essential. And these cases have to do with when you are plugging a piece of program into a larger program and you don't have control over the whole program or the API. GUIs is one place where that shows up a lot. a GUI library that someone else wrote you're using in your program, but it doesn't give you all the communication channels that you need. For example, this GUI is showing one fish's weight. It gives you a feed button and a feed 3 button. And when you click the feed 1 button, the 7 is supposed to go up to 8, or if you clicked feed 3, the 7 should go up to 10. And the code probably looks something like this. There is a weight variable that you might call the model of the fish here. And the fish starts out, this fish starts out at 0. And then when you create the GUI, you can make a button like the feed 1 or feed 3 button. That button has a callback function, and the callback function maybe receives an argument that is an event, where a mouse event that clicked the button, but it does not receive the current model. It doesn't receive the weight because the GUI library doesn't know about that. Instead, this callback function changes the weight model. It changes the variable, updating it to be 1 more or 3 more or 7 more or whatever. And then it also has to take that weight, turn it into a string, and update it. So what's going on here is that the GUI library doesn't let the callback function, it doesn't pass the current weight in or get the current weight out. And so the use of the GUI program needs a side channel to communicate the weight. And this is what state does in general. State gives the programmer a way of adding a side channel to a program. By side channel, I mean a way of having a function call over here, f of 1, affect what happens later when you call some other function, g, on 2, without, in the case when there's no value that flows directly from the result of f into the call of g, like this. So that's the good part of state. A programmer can add these new side channels at will to communicate among different parts of a program and plug them into different APIs. That's the drawback as well, at least if you're reading someone else's program. If you're reading someone else's program and there's state behind the scenes, you cannot see all the channels of communication, or they may not be readily available. And this is what makes programs that use state harder to maintain in some cases, because the side channels and the invariants related to those channels are not apparent. So state has some good parts and some bad parts. Clearly, in any case, it's an important feature of many programming languages, so it's something that we should study.